This is the 4.3 to 4.5 morning quiz review. Number 1, we're given a function. Find the average value on the interval, closed interval from 1 to 3, and then find the value of c guaranteed by the theorem. So first, if we want to find the average value, we can go through average value theorem. So average value theorem says 1 over b minus a, the definite integral from a to b of f of x. So we can clean f of x up a little bit here to get this function prepared for power rule so that we can find the antiderivative. So I can distribute the 4 through and then split them up into individual fractions, and I get 4 plus 4x to the negative 2. So my a value is 1, the b value is 3. So 1 over b minus a, so 1 over 3 minus 1, integral from 1 to 3 of the f of x function that's slightly cleaned up. Now we can go through our steps here. 1 over 3 minus 1 is simply 1/2, so that will stay put for now. We just have to find the indefinite integral for 4 plus 4x to the negative 2, and then we can plug in the upper and lower bounds. So a lot of students want to just directly plug the 1 and 3 into this function, but we haven't found the antiderivative yet. So the antiderivative have to be applied before we can work with these bounds. All right, so antiderivative 4 is 4x. 4x to the negative 2 becomes 4x to the negative 1 over negative 1. Remember, we're adding 1 to the exponent, and then we're evaluating between upper and lower bounds from 1 to 3. Upper bound gets plugged in first, so 3 gets plugged in for the x's, so we get 12 minus 4/3 minus, then we plug in the lower bound, plug 1 in for the remaining expression, so 4 times 1 minus 4, and then there's a 1/2 still sitting out there in front, so it's just a matter of trying to keep track of all these pieces here. So 12 minus 4/3 is 36 over 3 minus 4/3. Well, actually, I combine this to be minus 8, and so 12 minus 8 is 4, and I just found a common denominator, minus 0. I'm sorry, the 4 minus 4 cancels out to be 0, so 12 minus 4/3 is the only remaining expression. Common denominator, so 12 becomes 36 over 3 to match with the 4/3 here, and then combine that to be 32. 36 minus 4 is 32 over 3 times 1/2 is 16 over 3. So this is the average value. This is the average height of the graph of the function from the interval from 1 to 3. Now if we want to find the c value that guarantees it, we can just set the original function equal to the average height, or the average value. So the function is 4 plus 4x to the negative 2. We set it equal to the average value, and we just solve for x. Subtract the 4 over, and then cross multiply. 16 over 3 minus 4 is 4/3. So cross multiply, we get x squared equals 3, so x equals plus or minus root 3. But our c value has to be a value that sits between the interval from 1 to 3, so we only can keep root 3. Okay, number 2, f of x is the definite integral from 3x to the 4th to negative 5, 5 over 2 root t dt. Find the derivative of this function. Now, if we want to find the derivative of a function that has a definite integral, we're going to use the second fundamental theorem of calculus. So, as a reminder, second theorem tells us that if we have this setup where we're evaluating the derivative and the integral together, these two operations essentially cancel each other out. We do have some residual effect from this p of x. So what happens is that this p of x gets plugged into f of t, so f of p of x, and then that p of x is also being affected by the derivative, so we have to also multiply by the upper bound's derivative. This is assuming that the constant is in the lower bound and the variable is in the upper bound. If these are out of place, we can always flip the bounds and then pull a negative outside. So let's look at number 2 here. All right, we want to find the derivative, but notice that the variable is in the lower bound, so I'm going to flip the lower bound with the upper bound and then pull a negative outside. All right, so we want to find the derivative of this expression, so we should have to work with the rule. The upper bound gets plugged into the original function. Essentially, this function is going to remain unchanged. We're not going to apply derivative or integral of this simply because these two operations cancel each other out. So 3x to the fourth gets plugged in for the t. So negative 5 over 2 square root of 3x to the fourth times the upper bound's derivative. So 3x to the fourth becomes 12x cubed. And if we clean this up, we get negative 30x cubed over root 3x squared. And then simplify some more, negative 30x over root 3. All right, number 3, here's our function. Now notice that we want to do the same thing, second theorem, but both upper and lower bounds have variables. So since that's the case, we can just apply second theorem once for the numerator and then minus, and then do the same thing for, once for the upper bound and then once for the lower bound. So we can essentially just apply the second theorem twice. So let's walk through that procedure. Upper bound first, so upper bound gets plugged into the t squared minus 2t, so x minus 2 root x, multiplied by the upper bound's derivative. That's the p prime here. So the derivative for square root of x is 1/2 x to the negative 1/2. Minus, and we do the same thing for the lower bound, because lower bound also has a variable. So plug lower bound in for t squared minus 2t, so 4x to the fourth plus 4x squared, times the lower bound's derivative. So negative 2x squared becomes negative 4x. Okay, so we've essentially found the derivative. We just have to clean this up a bit more. I distribute the x to our the 1/2 x to negative 1/2 through, and then distribute the negative 4x through, and here is the answer. Okay. All right, number 4, we have a definite integral from negative 3 to 6 is equal to negative 4. Integral from 0 to 3 of the g of x is equal to 2. All right, if g of x is even, meaning that the graph is symmetrical about the y-axis, find the definite integral from negative 6 to 3. All right, now we can sketch this portion here. From negative 3 to 6, we want the net sum, or the net value, to be negative 4. So I'm going to create a graph here with the origin at 0, 0, and I'll just space everything out evenly. Negative 6, negative 3, 0, 3, and 6. Okay, so the net accumulation from negative 3, okay, to positive 6 is going to be negative 4. And along the way, I need to make sure that the graph is symmetrical about the y-axis. All right, let's look at this here. Maybe this will be more helpful. From 0 to 3, definite integral is 2. So from 0 to 3, we know the net sum is going to be positive 2. So I'm going to just create a little portion and call that area 2. Now, if this portion is 2, then we know this portion from negative 3 to 0 must be 2 as well. Otherwise, we can't have a graph that's even function. Now, from negative 3 to 6, we want a net sum of negative 4. So this is already positive 4. So if we want the net sum from here to here to be negative 4, we need this to be a larger negative value, so that when they add up, they will reduce to be negative 4. So we need this to be negative 8, because 2 plus 2 minus 8 gives us negative 4, so that matches. Okay. Now, if this portion is negative 8 from 3 to 6, then we know that from negative 6 to negative 3 must also be negative 8, because we have to maintain symmetry about the y-axis. All right, so now once we have this graph sketched out, we should be able to solve this problem here. From negative 6 to positive 3, we just have to total these up. So negative 8 plus 2 was negative 4. All right, same scenario, but now we want the graph to be odd. So odd is going to be a function that is going to be symmetrical about the origin. So basically, as long as we're same distance from the origin, we're always going to have values that cancel out to 0. So again, we have from 0 to 3 is positive 2. So we know this portion is positive 2, and this is positive 2. Odd function has to cancel out from negative 3 to 3. So we need this portion to be negative 2. All right, we want from negative 3 to 6 equals negative 4. So we want this entire portion to be negative 4. Negative 2 plus 2 is 0. So that will remain. This must be negative 4 if we want the total of these three areas, or these three definite integrals, to be negative 4. So then if this portion is negative 4, then we need this portion to be positive 4, because if g of x is odd, then the net sum from negative 6 to 6 will cancel out to be 0. So this must be positive 4. And now we can solve this question here. The definite integral from 0 to 6. So from 0 to 6, it will just be 2 minus 4, which is negative 2. Number 5, evaluate the indefinite integral of square root of tangent x secant squared x dx. We may have to go through use substitution. So we can rewrite this as tangent of x to the 1/2. If we write it as tangent of x to the 1/2, usually our first guess, if we're trying to determine what the u value is, we want to choose the portion that sits inside the parentheses. That should be our first guess. So if we let tangent of x be the u value, let's see if that will work out. So we'll let the u value start off with tangent x. Okay, it's a bit of trial and error here, but this is a good place to start, especially if you see a parentheses raised to an exponent. So what's inside the parentheses? We'll let this be the first guess for the u value. So the u value is tangent of x. We need to find the derivative of u with respect to x. So du over dx, the derivative for tangent x is secant squared x. Looks like we have a nice match with the secant squared x. So I'm going to solve for dx. So solve for dx, I get du over secant squared of x. Okay, so go through and make my substitutions. Tangent x gets replaced with u to the 1/2. Secant squared x stays. Replace dx with du over secant squared x. Secant squared x cancels out. The entire point of going through u substitution is we want to convert everything to be in terms of u, and along the way make sure that that any remaining derivatives are mashed up and taken care of. So we have integral of u to the 1/2. So now we can go through power rule. So 1/2 plus 1 is 3/2. So u to 3/2 over 3/2. Flip the 3/2 as 2/3. So 2/3 u, 2/3 tangent x to 3/2 plus c. All right, number 6, we have the integral of 2x square root of 4 minus x. If we rewrite this using parentheses, I get integral of 2x times 4 minus x to the 1/2 dx. So we'll let the 4 minus x be the first guess as the u value. So we'll let the u value be 4 minus x. The derivative of u with respect to x is negative 1. So dx equals negative du. If we make our substitutions, the 4 minus x gets replaced with u. The dx gets replaced with negative du, but there's still an x that does not go away, does not cancel out. So we have to go through another set of substitution. So this is the change of variable, where since we have an assigned relationship between u and x, we can solve for x in terms of u. So if I solve for x in terms of u, x is equal to 4 minus u. If I make that substitution, 4 minus u gets plugged in for the x. Now I have everything in terms of u. I can just distribute everything and set it up for power rule. So distribute this through. I get negative 8u to the 1/2. The u's combine to be u to the 3/2 along with the 2, so plus 2u to the 3/2. Both terms are set up and ready, prepared for power rule. So now we can apply power rule. Add 1 to the exponent, so 1/2 plus 1 is 3/2 over 3/2. 3/2 plus 1, the same thing as 3/2 plus 2 over 2, so 5/2 over 5/2. Flip the denominators up to the top, and we get negative 16 over 3 and 4 over 5. And now we can replace our u back in terms of the original variable, which is x, which is 4 minus x. And then don't forget the plus c. Okay, number 7, we have the definite integral of x squared, x cubed plus 1 cubed from 0 to 1. Again, going through u substitution here. Going to let the portion in the parentheses be the u value. So u is x cubed plus 1. The derivative is 3x squared. So dx equals du over 3x squared. Let's substitute the x. We're going to convert everything to be in terms of u. So x cubed plus 1 gets turned into u cubed. X squared stays initially. Dx gets replaced with du over 3x squared. The x squared cancels out nicely. We're now left with the definite integral, or indefinite integral, of integral of u cubed du with a 1/3 out in front. So from here, I can either convert this to be in terms of x and then plug in upper and lower bounds, or I can convert the bounds to be in terms of u, and just solve and just find the depth integral in terms of u. So we have a assigned relationship here between u and x. So if I plug 0 in for the x, I can solve for u, right? So if I plug 0 in for x, u cubed plus 1 is 1. So my new u value that was originally as the lower bound x becomes 1. My new upper bound, if I plug this x converted to be in terms of u, 1 cubed plus 1 is 2. So 1 plus 1 is 2. So that's my new upper bound and my new lower bound. So let's find the antiderivative. So u cubed becomes u to the 4th over 4. We can just directly plug the upper and lower bounds in because our bounds are in terms of u. So we get 2 to the 4th over 4 minus 1 to the 4th over 4. So 16 over 4 minus 1 over 4 is 15 fourths. Multiplied by the coefficient of 1/3 out in front, we get 15 over 12, which is 5 fourths.